Welcome to session number 5, operations and design. And I'll be the chair of the session because Rick couldn't make it. So you're stuck with me for the next couple hours. What is it? So our first speaker this morning, you've heard him already the last 2 days, 2.5 days. And he's a guy that when he speaks, you really should listen to him. I've learned an awful lot in the last 2.5 days listening to him. And I've been doing this for 45 years. So that says a lot. It's my pleasure to introduce Michael Milczarek. I was going to call him Mike Jones, just, for full transparency, because my name's Smith. So I have difficult time with last names. Mike, all yours, and thank you very much for being so generous this week with your time.
Yeah, thank you. Thanks, Mark. Okay, so this paper is actually Angel Breseño's paper. Unfortunately, he's on a project right now in Peru, and he couldn't make it, so you're gonna have to put up with me. This describes Angel's graduate work. He worked with us in our lab, and I'm going to go over some of the results of the experiments he did and what it means for us. I'm not going to present everything he did, just give you a slice of some of the things. Okay, so the question is that we know there's mines, and there's a lot of them, especially in copper, where they do initial ramp up irrigation. So you start out slowly and then you increase over time. And based on experience at individual mines, this is very beneficial. It improves the recovery. And so the question is, why is that? And so the hypothesis that we had was that irrigation ramp up improves moisture distribution within the leach ore and prevents near surface ore collapse. So this aerial on the side here, you see all these little dots. Well, these are saturated ponds that are proximal to the drippers. This is a crushed heap leach ore, 1/2-inch agglomerated copper sulfide, secondary sulfide. And you can see some of what they call paneles here are fine. There's no ponding, others there's just massive ponding underneath every dripper. And even though some have ponding there. So what does that do to the process? And, we talk about least efficiency. What really we're focused on is inefficiency. And this is because you have heterogeneities with the ore, even with a crushed ore sample and agglomerated, and you develop flow networks. Okay, you can have low K, by K I mean saturated hydraulic connectivity, uneven wetting. You can get ponding and perching not only at the surface, but at the bottom, and preferential flow and channeling. So if you start having preferential flow and channeling, then that really reduces the efficiency of your operation because you don't have a nice even distribution of solution, and it's going to affect your recovery. So the experimental approach we took on this is we got about a ton of leach ore, and big shout out to BHP and Freeport that provided the ore for this experiment. And that we wanted to have a leach ore that had marginal hydraulic properties, and I'll talk about that, what that means in a minute. And so, in other words, we know it has the potential for some permeability issues. The ore was agglomerated with raffinate at 0.06 grams per gram, 6%, and concentrated sulfuric acid at 6 kilograms of sulfuric acid per ton of ore. And this is the recipe that the mine uses. Cured for 1 to 2 weeks. Then we conducted consolidation permeability tests. These are small diameter cell tests to evaluate the hydraulic property changes under pressure. And then we packed columns or one column, a series of one columns at 150 centimeters tall by 54 centimeters in diameter with the agglomerated and cured leach ore. And the initial target bulk density was 1.5, and basically a conveyor stack type system, very, very soft bulk density. And then we conducted 3 different irrigation ramp up scheme tests. And so we had 3 different columns. And we use a single drip emitter. So the whole point of this was to simulate, when we looked, we developed the diameter of core that we're going to use was to simulate a 1 meter center on the drip emitters. Okay, I'm pressing it really hard. Can you manually advance that? Okay, great. So this is the experimental design. So of course, because we are instrumentation guys and we love all kinds of sensors, we loaded the column up with sensors. So we had water content sensors and tensiometers, or what you can call capillary pressure sensors at different depths, typically about every 15 centimeters down in the column. We put in a bunch of ERT sensors and worked with Dale Rucker from hydrogeophysics on that. I'm not going to present that data. That's another paper. We also have a neutron probe that we were running up the side of the column so we could measure what the water content in the column was. And the target irrigation rate was 9.1 liters per meter squared per hour. We also measured the ore collapse at the surface over time. And then the three different ramp-up schedules we looked at was a target irrigation rate, so we just started irrigating right at the target irrigation, a slow ramp-up, so 1/16 of the irrigation rate over 48 hours. And what that basically means is you irrigate at the leach rate for a half hour, and then you let it rest for 23 hours. And so this was I can't remember exactly what the full length of time, but this is about 2.5 weeks to get up to the target rate. And this fast up ramp up test was about a week to get up to target rate, but it's on-off irrigation. And that's what they do at the particular property that we were working at. Next slide. Okay, so I want to talk real briefly about consolidation permeability tests. These are the results. So we have two different things going on here. This is the saturated hydraulic conductivity on the x-axis, and then this is the estimated heat height. And this is calculated basically on the pressure, the consolidation pressure that we applied to the leach ore, and then we run a saturated hydraulic conductivity test. So with the KSAT, it starts off, it's got a very high saturated hydraulic conductivity, around above 10 to the -1. It starts to drop off. Excuse me. And by the time you get to 18 meters, you're down around 10 to the -3. The what we call the safety factor, the 100x times the saturated hydraulic conductivity, or the irrigation rate, is right around here. So this tells us that for this particular leach ore, they're probably going to start approaching the efficiency of the hydraulic capacity, or at about 5 meters, or let's call it 5 to 6 meters is probably a good lift height. But in the near surface, which is what we're interested in, the permeability is quite good. This is the bulk density curve on the second x-axis up here. And you can see it starts off very, very light bulk density, and then it ramps up very quickly by the time we get to 5 meters. And this is 5 meters in the heat. Okay, so you've got all this overburden pressure. By the time we get down to 5 meters, we're around 1.8. That's usually kind of a bulk density beyond which you might start having problems. By the time you're at 10, you're almost at 2 grams per cubic centimeter. Very high bulk density, you're definitely going to have problems. Next slide. Okay, so this is what we're looking at here. This is a picture of the column. This is very shortly after the irrigation was started, and this is with the full irrigation test. We start to see a collapse zone. And then by the time the test was ended, the ore had collapsed quite a bit throughout the column. And so what we're looking at here on this graph is this is time. This is the depth of collapse. And so this graph right here, or this line right here, is what's happening in the center down here. And this is what's happening on the side. And so the collapse here was close to 20% in the center. We had over 25 centimeters of collapse in the middle. and around 15 centimeters of collapse in the along the sides along the bank. Next slide. Now this is looking at it again, time here. This is the collapse. And so here we have the 3 different tests. And so this very first one is, this shows the collapse with full irrigation. And wow, man, within 24 hours, it had completely collapsed. This is the, this is in the center, this is in the side. Now the test number 2, which was the very slow ramp up, there was no difference between the inside and the outside collapse. It collapsed very slowly, and we got down to about 10 centimeters, which is about a 5 to 6% settlement, which is, that's probably ideal in a heap leach environment. And then the fast ramp up test had an intermediate collapse where basically this is on the edge and this is in the center. Next. So after the test was over, we took core samples. We scalped basically the ore down in 15 centimeter increments, took core samples to estimate the bulk density. And this is kind of the average bulk density across. So here is the full irrigation test number 1. This is test number 2. And again, we've got this solid and dashed lines where the solid line is the middle and the dashed line is on the outside. We see no difference in the slow ramp up, and the fast ramp ups is more intermediate. But you know, down at 100, essentially 120 centimeters, we're seeing bulk densities of around 2 in the fast irrigation. So significant amount of ore consolidation. And the only difference here is the irrigation rate. They were packed exactly the same. Next slide. This is moisture content. So these are all the different sensors. This is kind of a busy graph, hard to describe, but what you see again is this is full irrigation. Within 24 hours, you get a massive increase in moisture content. Again, these sensors are directly underneath the emitter, okay? And what's interesting is that we got solution contents of above 0.2, and in almost all the sensors, except for a few, we got very high solution contents, and then they declined and went down. And I'll talk about that in a minute. And then there was one sensor here around 75 centimeters where it finally started to go back up. But the highest solution content was at 15 and 30 centimeters. And then we also saw these jumps in the data in looking at the short period of time. And we suspect that those are due to actual points in time where things collapsed. Okay, and so we're seeing this big jump in the water content, a big change in the water content. Next slide. This is the slow ramp up test. And so you see that the moisture content goes up rapidly and then declines during the period of rest. And it goes up like this. And so we see this gradual increase. Again, these sensors are below the emitter. We see this gradual increase in moisture content. And almost all the moisture contents, except the 2 at the very bottom, show a moisture content below 0.2. So we're showing much lower moisture contents in the center of the column. And then we're seeing the higher moisture contents at the very bottom. Now, this is the classic theory. This is what you would expect based on consolidation permeability testing. The most pressure is down at the bottom of the column. And that's where you would expect for the ore to have the greatest density, and that's going to result in a higher moisture content at an equivalent irrigation rate. We saw no declines in the solution content, just kind of a steady rise, and then slower wetting front at depth. And also, okay, next slide. And then for the fast ramp up, here we saw this up and down in the water content, but the you know, we were basically up in 120 hours, so basically around 5 days, we were at the full irrigation rate, and we saw fairly high water contents, but actually the lowest water contents were at the near surface, 15 and 30 centimeters, so kind of surprising. And again, lower wetting front at depth. Next slide. So at the end of the test, we ran a couple of tracers. One was a dye tracer, and then we ran a bromide tracer as well. So we could look at fast flow versus stagnant flow versus preferential flow. And again, I'm not going to talk about that. That's another paper. But what's really nice with the dye test data is that you can track where the solution went. Now, rhodamine was used as a dye. It has a retardation factor, so we only could run a certain amount of dye before we would have run out of raffinate. So it's not as long as we would have liked it, but we were basically able to get the dye down to the greatest depth. We're looking at when we pulled the material off, we were able to see the dye, and we're looking at 0 centimeters down to 120 centimeters in depth. And so at 0 centimeters next, we see a small area just below the emitter that was wet, even though the whole thing had collapsed. So it's like, what's going on? At 20 centimeters next, you could see that there was quite a bit of lateral distribution. And so there was wetting through most of the center of the core. Next. But then by the time we get to the 30 centimeter, that center of the core had started to fade and go away. And then we're seeing this ring of solution on the outside. Next. And then so when we're down to 50 centimeters, we don't see any solution going through the center of the column, and all the solution is being pushed to the outside. Next. And then finally, when we get down to 120 centimeters, basically you've got, and Angel calculated this based on some digital analysis, but I don't remember what it is, but let's say 5%. The majority of the solution is going through 5% of the column area. Okay, tracer test 2. Next, again, we see similar type of flow concentration right there below the dripper. But again, this system didn't collapse. Next. So nice lateral distribution, similar to what we saw in the first test. Next. It continues down. Next. And then we're seeing very similar wetting patterns as we do at up in the near surface, whereas at 50 centimeters that had disappeared with the fast irrigation. Next. And so then as we go down next, we see that lateral distribution, or at least the dye diminishing, but it's still below the emitter. Next slide. And we see actually a similar pattern for test number 3. Next. And in this case, which was really interesting, we didn't see much dye penetration as well. And that was also, the water content that we saw at 15 centimeters was quite low. So we're not quite sure how the water got in there, to be honest. But next. But once we get down to 20 centimeters, we see it. Next. And again, we see similar patterns, but again, it's a little more, it's not as dark of a blue as we saw in test number 2, which is the slow ramp up. Next. And so on. Next. Next. Yeah. And so then by the time we get to the bottom, it's a little bit moving around, and it's not quite as uniform as what we saw in the slow ramp up. Next slide. So what does this mean? So we know from the ERT analysis as well as the neutron probe analysis that there's quite a bit of variability in the outside part of the column. And what was also interesting was that in the fast ramp up, we could see it was very distinct. And I didn't put this in this presentation just for the sake of time, but with the neutron probe data, you could see that it was dry at the surface and very dry at the bottom. And then there was this bulge in the middle of moisture content. And then if you just look at the mass balance, which we were tracking by what we're putting in, what was coming out and accounting for evaporation, what we see is that with the test number 1, there was a big jump. And this is storage, by the way, I'm sorry, in terms of total liters within the column. We see a big jump in test number 1, and then it drops off, and then it slowly starts to come up. And that's consistent with the water content sensor data. With test number 2, the slow ramp up, and we see much more accumulation of storage and higher storage than in test number 2. Excuse me, test number 3, which is the fast ramp up. So between these tests, even though we use a much longer time to ramp up, and what we saw is that the slow ramp up actually had more storage. So that tells us that the solution distribution within the ore is much better. So it's moved out, and there's more mass of solution. So there's more contact of the raffinate with the ore. Next slide. So what's our conceptual model here? Next. So under full irrigation startup, what's happening is, if you do the calculations, what's happening underneath the emitter is, and I don't recall, but you're getting more than 100 times what your calculated irrigation rate is. So at 9 liters per meter squared, per hour, you're actually applying more on the order of 100 over that little spot. So that's just pushing a massive amount of water into the leach ore. You're getting the small and the medium pore saturate. You get loss of the particle. If the agglomerate is not holding together, you could get movement, and you lose your soil strength, and the thing just collapses. And so what happens is what we saw in the dye test. The solution goes down and then has to go around. So you get uneven wetting, dry zones, less storage, and poor solution distribution. Next. Whereas ramp up, putting that irrigation on for a half hour, an hour, and then let it rest, well, that allows capillary forces to pull the water out, and you actually may get a bigger wetted zone initially. And then the next time you come on, this is the thing about unsaturated hydraulic conductivity. It's a function of the water content. So if you have a very dry material, it is not going to be able to carry water as fast as a material that's more wet. And so as you pull that water in, you're increasing the hydraulic conductivity of your leach ore. And so the next time you irrigate for an hour, you get a bigger bulb. And then the next time you get a bigger bulb. And so you get much better solution distribution with the ramp up. And you maintain the ore structure as well. Next. So in conclusion, test 1 with full irrigation showed the strongest ore collapse, pawning preferential flow below 30 centimeters of depth. Test 2, minor collapse, highest storage retention, better solution distribution. Test 3 showed an intermediate behavior. And, just so as a general comment, and Dr. Mike Yao had a paper yesterday where talks about some of the other test work we've been developing to look at this problem. Your best ramp up scheme should be ore specific. And you need to take a look at the hydraulic properties, do some collapse tests, and simulations will help you. Thanks.
We have time for one question for Mike. No, you've answered everybody's questions. I spent my entire career trying to do that. You did it in one morning. Oh, sorry. I'm terrible at this. I keep insulting people by not seeing them. It's because I'm old.
Good morning. Thank you for the presentation. It was great. You got me thinking about, that initial step up, but then there's some sites that do pulsing. When pulsing is being done, would you recommend also to do a step up procedure, or once the ore has been wet, you already created those paths and you can just, instead of ramping up, you can just go up into irrigation, full irrigation?
Can you define what you mean by pulsing?
Pulsing, so some techniques out there, you turn it off for a month and then you come back to it, and due to either solution balance or a sulfide leaching technique.
Yeah, I think that once you've wetted the system up, and what the slow ramp up does is it helps you get more uniform wetting and it creates less preferential flow. There's no doubt about that. But once the system's wet, you can do whatever you want. One useful thing about on-off ramping, on-off, or what you're calling pulse irrigation is that, especially with a copper heap leach, if you're towards the end of your leach cycle, and you can take it off for a month, and that'll actually let it drain out. That actually improves your air permeability, allows you to get more air, and those kinetic reactions will still be going on. And then you come back in and you irrigate, and then you push that copper that you've reacted. So it's the pulsing is very useful towards the end of the cycle. The ramp up is important in the beginning to get better solution distribution.
Thank you.
Yeah.
Thank you very much.
Thanks, Mark.
So our next speaker is Wenying Liu, who will be talking about iodine-assisted leaching of chalcopyrite. Oh.
Morning, everyone. Thank you for being here today. So if you were at the keynote speech this morning, the last question towards the end of the talk is what do we do with the low-grade chalcopyrite ore? So my talk today is going to focus on leaching of the low-grade chalcopyrite ore. And this work was done by Ronnie Winnacle. Ronnie was one of my PhD students, co-supervised by Dr. David Dressinger at the University of British Columbia in Vancouver, Canada. And I put another co-author here, Akira Miura. Mr. Miura is a sponsor at GX Nippon Mining Metals in Japan. So as Mark mentioned, my talk today is iodine-assisted heap leaching of chalcopyrite, laboratory and modeling studies. So I hope this works. Oh, okay, so as we know, the demand for copper has been increasing. At the same time, the grade of the ore has been decreasing with elevated concentrations of impurities. So it might no longer be economically feasible to treat this low-grade primary copper sulfide by conventional flotation than the pyrometallurgical processes. So direct heap leaching of primary copper ore can lower the production cost. So one way to do this is by adding iodine to the solution, to ferric sulfate solution, which has been reported to accelerate the chalcopyrite leaching kinetics. And so GX Nippon has patented this technology. So back in 2017, they approached us to sponsor us for a 4-year project to model the response of leaching of the low-grade primary copper sulfide ore in this iodine process, and ask us to simulate the performance of this process in an industrial heap leach. So we first identify the gaps because it's already a patented technology. And then that's the gaps we identify here. The kinetics of the iodine-assisted chalcopyrite leaching in ferrous sulfate media was not well studied, so I'll report the results in our study. And it's also not well understood whether chalcopyrite surface would passivate in the iodine-assisted process. As we know, the challenge to directly heap leach chalcopyrite in ambient temperature because of the passivation. And the kinetics is very slow, is very different from oxide and secondary sulfide. So it also is essential to scale up the process from the laboratory to a pilot, eventually to a commercial scale heap leach. Okay, so these are the objectives we defined in the project. First, we want to develop a kinetic equation for this process by collecting and interpreting on kinetic leaching data. So these reactor tests were done under fully controlled conditions, including pH, ORP, and temperature. And after that, we collect the leaching residue under different leaching conditions to study the mineral transformation and morphology change during leaching after, just to get an idea whether passivation occurs and what is the leaching product, whether pyrite reacts or not. So, and then the third objective is to simulate the 1 meter and 6 meter column leaching test and to evaluate the performance of copper extraction to variations in different design and operating parameters such as irrigation rate and ferric concentration. So this is the reactor design here, and you can see here, this is a controller, and this is a fully controlled reactor test. And let me see here, so we have a pH potential probe here, and this is a water bath to control the pH, to control the temperature. And then we have the sulfuric acid, and we have the potassium permanganate just to control the pH and ORP during leaching. So control as is a constant. And to study the morphology and the mineral transformation, so we use the XRD and the mineral liberation analysis to understand what's happened to the mineral surface during leaching. And so the samples used first is a washed chalcopyrite concentrate. This is prior to leaching as the control, and also several leaching residues collected under representative leaching conditions. Okay, and this is the column leaching test. As you can see here, we named this as a Hitachi 1 meter column. So these tests were done in Hitachi, Japan. And this is a 10 centimeter in diameter, 1 meter column height. And you can see here control test in the absence of iodide. We didn't add any iodide in the control test, of course. And then this 2 column test with addition of different concentration. Here's 100 milligram per liter and 200 milligram per liter of iodide to first sulfate media. And you can see the irrigation rate there, and I didn't put particle size. Particle size, I believe, about 80% passing half inch. And this is a Chile, we call Chile 1 meter column. So these tests were done in Chile. And then the third column leaching test is 6 meter column, 15 centimeter in diameter. And you can see this is the control test. And this is total iodide concentration uses 100 milligram per liter. And next, please. And so these are the results. This is the reactor leaching test done at EVC. And here you can see this is an increasing potential. The standard condition is here. So the increasing potential at a constant iodide concentration is 150 milligram per liter. And you can see here as potential is increased, and you can see copper extraction increased, and at a highest potential tested, this is versus standard hydrogen electrode. So you can see here, this is the highest potential tested, and you can see you can achieve 100% copper extraction. And this is a different concentration of iodide, and this potential is a constant. This all of the here temperature 25 degrees C, here 25 degrees C. So you can see this is a control in the absence of iodide, and you don't see much extraction here. And as the iodide concentration was increased, and you can see a significant increase in copper extraction, and it's a complete extraction was achieved. This is probably at about 150 and 200 milligram per liter of iodide. And we also study the effect of temperature. So 25 is our reference temperature, then increasing to 40 degrees C. And you can see here, very interesting here, we did the temperature, different temperature tests at 2 different potential here. And this is the low potential, this is the high potential. And you can see here for the low potential, we increase the temperature to 45 degrees C. Still, the extraction is pretty slow. And when we increase the potential to higher value, and you can see the temperature effect as the temperature increases, the kinetics increases much faster. So the key point that I'm trying to make here is for the iodine process, in order for the temperature effect to manifest, you have to get the potential high enough in order to see the temperature effect. The reason is, I didn't present this, the reason is about the iodine speciation. So you have to get the potential high enough in order for the active iodine species to be the predominant species. In this case, is triiodide, I3 minus, and diiodine, which is I2. So these 2 species are responsible for chalcopyrite leaching to occur. If the potential is too low, then the predominant species is the iodide, which is the I minus, and that's not very useful for chalcopyrite leaching. So here I put the pH result just to make the point. If you look at these 3 tests were done under higher temperature, 40-45 degrees C, and we started seeing iron precipitation to happen. Because whenever you see iron precipitation to occur, then you probably start worrying a little bit and see whether this iron precipitate could coat the chalcopyrite surface and start to passivate the surface. Next, please. So after we get a reactor leaching test, and we derive a kinetic equation. So this kinetic equation is part of the comprehensive heat leach modeling. So that's why this kinetic equation right is very important. So we don't need to look at the details of this equation, but the point of this equation is you have X, which is copper extraction, as the model output basically, and this shows the copper extraction as a function of temperature. So we've done a bunch of tests on temperature, and this is the first ratio, which represents solution potential. Here is the iodide term here. So we have alpha beta here to represent the effect of potential on iodine speciations. You have different potential range, and you have different active iodine species. So we use this kinetic equation. We're able to describe the kinetic data. And following this, next please. So we did XRD, XPS, and MLA tests to study the mineralogy change during leaching, as you can see here. So this is just a chalcopyrite concentrate sample here, and you can see the peak. This is chalcopyrite, nothing happening, right? This is the sample we put in the leaching. Here is this tool is in the absence of iodide addition. You still see the same chalcopyrite peak, not much leaching going on in the system. And this one is 669 millivolts, 25 degrees C in the presence of iodide. But as we mentioned, because the potential is low, so you don't get the active iodine species, and then you still see the peak for chalcopyrite, and you don't see much extraction going on there. And this is 769 millivolts, and this is in the presence of iodine, and you can see that the chalcopyrite peak disappear here because leaching occurred to a large extent. And so if we look at this is the 669 at a higher temperature, and because the potential is low, you don't see much leaching, but you started seeing iron precipitation, and you started seeing a different peak. So here is iron precipitation. So we did the MLA analysis to understand the transformation of mineralogy here, and this is just the chalcopyrite sample. The blue here represent chalcopyrite, and you see some pyrite in the concentrate here. And this is without iodine, not much leaching going on. So you still see very similar to the sample here just chalcopyrite. And here, this is in the presence of iodide, and the potential is right in the right range. And you started seeing this red color here that's that represents elemental sulfur formation. And you still see the, the yellow here, that's pyrite, and pyrite is inert. Pyrite is not active in the process. You cannot leach pyrite there. And here, again, potential is not right here, even though you add iodide in the system and you don't see much leaching. But interestingly, you started seeing some orange color here. That's precipitation of jarosite as the arm precipitate. And this is more obvious here at 40 degrees C. Here you see quite a bit of orange color that represent the formation of iron jarosite precipitation. So even though elemental sulfur is formed, jarosite formed, but both didn't passivate the chalcopyrite surface. As you can see, leaching was able to reach 100%. So next is the column leaching test. And you can see here, this is the control. And here we don't see much leaching going on here. And by adding different concentration of iodide, you started seeing extraction. So here, the tests were just run for 125 days, and they stopped the test at this point. So, but you can see that the leaching is still ongoing. And then you can see here similar. And here I wanted to point out the potential trend you can see here. And this you can imagine when you irrigate solution, the solution would percolate through the column. Towards the end, you run out of ferric and you started seeing potential drop. And this towards the bottom of the column, that probably similar to conventional ferrous sulfate leaching. So I see the chairs here. I have one last slide. Next, please. And this is just a modeling work. We're able to model the data, and you can see the decrease in the rate constant from this 1 meter column to this. And then the reason is because the ratio of iodine to solid or chalcopyrite decreasing, and then the 6 meter column, the rate constant is even smaller. And after this, I think next is my last slide. And so here shows the effect of irrigation rate, ferric concentration, iodide concentration, and temperature. So the point here is by increasing irrigation rate up to a certain extent, you can see an increase in copper extraction. But of course, beyond a certain point, you no longer see the beneficial effect. So that's kind of simulate the height of the heap height, and how would that affect the extraction. Is really when you have a taller column or taller heap, you need either increase irrigation rate or have a right to ferric concentration. So last one. So these are the conclusions. The chalcopyrite can be leached with faster kinetics in the presence of iodine in ferric sulfate media at ambient temperature. And the process performance is mainly controlled by solution potentials. That parameter has to be right. Kinetic analysis also the leaching is controlled by surface chemical reaction. Elemental sulfur is the leaching product, iron precipitate forms, but they don't passivate the surface. Simulation indicate that there are optimum values of design and operating parameters. Beyond this optimum value, you no longer see beneficial effects. So, and that's, if you can, the last, I wanted to acknowledge GX Nippon Mining Metals to support us for 4 years to do this work. And the column leaching data were provided by GX. And thank you for your attention.
We have time for a couple of questions. Now the lights. Nope. Nope. No questions? Oh, wait. Oh, sorry. I can't see out of this side of my head today. Oh, yours.
Did you have to aerate the columns, or were you adding potassium permanganate to the columns to control the oxidation state?
For the columns, we have a separate container for potassium iodide and another container for ferric sulfate solution. So you irrigate provide the two solution into the column. And that's the original idea for a real heap leach as well. So you have to have two irrigation lines and then provide solution to a heap. So the problem, because this has to be done right, because if you mix them outside of the column or side of the heap, that ferric could oxidize iodide to iodine. And iodine is, you need to be a little bit careful because at this temperature, heat, like close to even temperature might be fine. But if the temperature is a little high, that increase the vapor pressure of the iodine, you could lose the, iodine. So that's why, you have to supply the solution to column or heap into separate and let them meet inside the heap. So that generate the iodine or triiodide, and those we think are the active species for chalcopyrite leaching. Yeah. Thank you, Mark.
So our next speaker comes from Mendoza, Argentina, and I've had the pleasure of working with him on a number of projects over the last 2 decades, which sounds so long when I say it out loud. So I'll introduce Silverio Prota, who is going to talk about liner leakage.
Thanks, Mark, and thanks, everybody. You shouldn't have mentioned the 2 decades because that's an indicator of our age, but whatever. Okay. Next one, please. Okay, when we look at these, all these masterpieces, the first thought that comes to our mind is perfection. And although it's almost impossible goal to achieve, we always try to get as close as possible to it. Next one, please. So when we talk about liner installation, what would perfection mean? In terms of installation, would mean 0 leaks, right? Now, that triggers many questions. Is that even doable? If not, how far are we from getting there? What are the reasons that prevent us to getting into this goal? Which are the main variables that take into consideration here? And many other questions on the road. But it's very clear that if we want to get to a perfection goal of 0 leaks, it's important to know where we're going to get there and where we are starting from. What are the circumstances for not getting there? And in other words, we can only control what we measure, and the statistics that we share in this paper are here to provide some light on that road. Next one, please. So we have already introduced a little bit the purpose of this paper. We will add a few bullets on the next slides. We will, sorry, go backward. We will briefly explain the methodology of the investigation. We will share the results. We will compare to data from other papers. We will also share some conclusions, and please provide some questions and your conclusions as well. And we will thank some people, and we have a bonus track by the end of the presentation. Now, next one, please. So as we stated before, and as we've been discussing, one of the key goals here on these seminars is to share information, put aside our affiliations for a couple of days, and that's what we've done. So in this one, we are sharing information over the last 10+ years of electric leak location, and with the hope that it helps improving not only leak location, but also construction quality assurance and liner installation. If we are able to get that, then in turn, we will reduce the number of leaks. We will dramatically drop the risk of failure at least some of the aspects. And in turn, that will help us building trust and confidence in the society, because if we have less failure, then we will build trust. And as we mentioned yesterday, one of the key factors on getting the approval is, the environmental, social, and governance framework. Next one, please. So back in 2017, with Chris Baldiga from HGI, we have started having all of these questions about, how many leaks are out there, how many have we found? So we put together, our brains and came up with some statistics, some paper that is published. And now, 5 years later, we decided, okay, it's time to update this. And it's also a very good excuse to, get together, get out there, get some wine at Sparks. And I was surprised getting wine from Mendoza last night. Thanks for that. And we went even further, and we were able to not only get AGI data, but also we got the support from people from Chile, more specifically Innovacheck from the Membrane Tech Group. So I want to thank all of them for their participation in this paper and their support. Next one, please. So I don't expect you to even read this, but the main point here is that the huge dispersion in the data that we found. So, this is the number of total leaks per project. And as you can see, it's tremendous dispersion. On the left, we have the total leaks, and on the right, we have the leaks per hectare. So, we were not expecting 0 leaks, of course, as the average of, as the main value, but we wouldn't be expecting this huge dispersion either. In some cases, we get up to 10,000 leaks per hectare, which is 20,000 leaks per acre, roughly. Next one, please. So same as before, but just put it in a, table format. And here I want to point the standard deviation, as you can see, is 500, which is, more than 1 order of magnitude than the average value, which is telling you about dispersion. Next one, please. So now, in order to get some sense of what to expect, we put that on histogram way. The one on the left and the one on the right are quite similar, except that the one on the left is just by project, while the one on the left is by survey area, while the one on the right is by project. So we see, very few are on the 0 leak per hectare, both in terms of square meter or in terms of number of projects. And again, we see this dispersion. We have these guys here, over here, that are far and away increasing our average. This is not to scale, because it was very difficult. It was impossible to get it on scale and be able to present it on a PowerPoint. Next one, please. So, just as a first tool for you to take, this empirical probability graph is telling us, okay, what's the chances of getting, for instance, less than 3 leaks per hectare? Well, it's about 32%. And the chances of getting less than 10 is about 70%. But what worries me is that we have 7% chances of getting, extremely high, almost over 30 leaks per hectare, which would be double per acre. So that's far from perfection. Next one, please. So, on the previous paper, we were not able to split by different variables, as a recommendation from some of our colleagues and clients. So we started gathering more detailed information. So, so we split by, geomembrane material in this case, and the columns, the blue ones, is the total survey area, while the green lines are total number of leaks, and the red ones are leaks per hectare. Not surprised, given the booming on the lithium industry, that by far the LLDP is the first one, which is the one that's mainly used on lithium operation ponds. How are we doing on time, Mark? 7 left? Oops, okay, need to rush. But on the other hand, is the one that has, relatively high frequency. Next one, please. Same thing in, table mode. Next one, please. Okay, this is an interesting one. It's this is only based on 3 companies, so it's not the whole market, of course. And of course, 2020 was the pandemic, but you can see a significant increased trend in terms of survey area per year. Now, what worries me is that this increase in the number of leaks per hectare. We could expect this to decrease because we could say, okay, we are, evolving, we are improving, but no, we are increasing the number of leaks per hectare. Would this be generated by the booming in the lithium industry? Could this be generated by, lack of qualified resources? I don't know, but that's the data. Next one, please. So if we go by the type of facility, again, we know lithium evaporation ponds are the #1 in terms of square meters. Also, #1 in terms of leaks per hectare. While leach pads, it remains stable, same as ponds, but with the lower leaks per hectare rate. So that's a good for leach pads. Next one, please. If we go by country, and I need to clarify that in case of Chile, we have a much higher leaks per hectare, but this is data obtained from QC controls, which means the first barrier, the first control, while the other ones are QA. So this means that we have survey after the installation company has done their own QC. Next one, please. Same thing by country, but in a table format. Next one, please. Okay, cool. Sorry, previous one. Okay, this is one I like to highlight. We were talking about whether or not we have QA, QC on site, proper QA, QC. And the red guys are the ones that have, installation with no QA. And the blue ones are the ones that do have QA. Of course, we have some, high hits on the blue ones, but, as at first glance, most of the blue guys are on the lower portion of the graph, and many of the red ones are on the upper portion. And we have some zeros here on both sides, but just a few zeros. Next one, please. Well, same thing, but table format. And next one, please. Okay, now we have I'm not going to read through this. You can, read your own, but the point is that, it's said for some significant deviations that this is relatively consistent with, many other previous authors' papers and investigations. Next one, please. Now, we've gone through history, we've gone through statistics. Now, the next question is, have we found every single leak out there? And that's a big question, because if we haven't, then what have we do? What do we do to find them all, or to find as many as we can? Next one, please. This is a very useful document generated by our colleagues on TRI, and I recommend you to read it, especially for design and installation companies. Next one. And electricity, we want the electricity when we do electric leak location to just escape through the leaks, not to give them a free way to freely escape through access roads. And that sometimes it happens. Next one, please. So just very quickly, the ASTM requires us to, or suggests to have a, performance index of 3.0 when we do some certain calibration test, or above 3.0. In this case, it's a leach pad where we were having a perfect conditions for survey, and our ratio was 80, which is more than one order of magnitude above what ASTM recommends. Again, leach pad, perfect conditions, big site. Next one, please. This is the same leach pad, so similar ore, similar conditions, except that you can see a track over there, access road connected, and we were not even getting 3.0 as our calibration curve ratio. And of course, under these circumstances, we can still work, we can still find leaks, but most likely we will not find them all. We will miss a lot of them, and the size of the leaks that we will find will be much bigger than if we could have, good conditions. Next one, please. Okay, I'm not gonna read the conclusions, because we don't have much time. You can look at the presentation, but basically, it's the importance of leak limitation, CQA, and properly follow the recommendations. And zero leak should be our goal. Difficult to get, but we can get very close if we follow all the recommendations. Next one, please. These are some of the factors that take into consideration. Next one, which is the most important one. Well, we want to thank a lot of people, including Mark Smith, Abigail Beck, and some other folks that are out there, that make all these 10 or 15 years of leak location possible, because they trusted us, they gave us the opportunity to work on their projects and to be able to develop and investigate and improve our technologies and our techniques. Last one, please. And especially thank you to all the crew people that are actually doing the work while we sit here and speak. So that's about it. Thank you very much.
Thank you, Silverio, and we have time for one question. And lights are in that exactly the right spot. It seems you've answered all the questions, Silverio.
Yeah.
Very well done. Thank you. Thank you. Very, very interesting and in some cases somewhat disturbing statistics. So
It is what it is.
yes, exactly. Thank you. Oh, hang on.
Okay.
Yeah. Thank you. So our next speaker, we're doing this virtual, is that correct? Yeah. Okay, I haven't done this yet, so I don't know how this works. I guess I'll find out. So the next speaker is Zachary Felkey, speaking about new excess flow valves for preventing side slope washouts. And I have to say, I deal with side slope washouts all the time, and I love this idea. So I guess I give it to Melissa. Are you going to drive it now? How does it work? Okay, thank you. So apologies and bear with us while we work through our technical problems. Good visual, no audio, so.
Oh, sorry. Can you hear me now?
Yeah, that's fantastic. Excellent. Thank you.
Let's see if it's see if you can hear the video now. Let me know if you can. Thank you.
I can hear you speaking.
Can you hear it now?
No, nothing from a video recording, no. We see the slides.
I think,
Isn't technology wonderful? Sorry. Oh,
okay, let me try it that way. See if you let me know if you can't hear it.
So nothing from the video yet, just I hear you speaking fine.
All right, let me just go to the PowerPoint here. Okay, can you hear me all right?
Yes, loud and clear.
All right. So, sorry to start over again, waste a little bit of time there, but my name is Zach Felkey, a heap leach metallurgist at Newmont's Cripple Creek and Victor Mine in Colorado. So Cripple Creek has two heap leach valley fill heap leach pads, VLF1 and VLF2. So VLF1 was constructed from 94 to 2015. It has 4 drainages with internal ponds for each one of those. There's a max depth about 700 foot depth to liner. As this pad coned up, created quite a bit of side slope area, about 80% of it is side slopes of about 12 million square feet. The elevation being up in Colorado, we are from 9,500 foot to 10,400 foot in elevation for this leach pad. And of course, being up in the Rocky Mountains, we've got a lot of weather conditions to deal with, including high wind speeds, thunderstorms, snowstorms, freezing conditions, etc. So as this pad coned up, we created a lot of narrow benches as the first initial stacking, very aggressive back in the late 90s and right up to the extents of the leach pad, as you can kind of see on the outside skirts of the leach pad, which created narrow benches about maybe just big enough for a pickup truck. And very limited access, only one access road that goes up and down the side. So you have to travel quite a bit of ways on some of these benches all the way around to get to one end to the other. And it was stacked angle of repose, so about 1.4 to 1, so pretty steep. So as you can see from all of that side slope area, drip leach irrigation was used mainly due to freezing weather conditions. So we couldn't use sprinklers or wobblers, that sort of thing for about 8 months out of the year. So of course, with drip irrigation and side slopes, there's a lot of potential for washouts. So the wind can carry the drip tubes, or just the weight of the ore if it wraps over the top of the drip tubes, or you can see some of the pictures, there's a bit of ice that can pull down on the drip tube. That can cause a lot of strain on the connection between the drip tube and the adapter. So when these pop-offs do occur, these separations, they can blast that water out straight towards the side slope, or just create a pond right in front of the side slope if you have a berm there, and then eventually it wash out pretty quickly, depending on size fraction of your ore. So impacts of the washout, obviously geotechnical safety hazard of that ore being moving across access roads and down numerous benches. You also have environmental hazards with process solution potentially exiting the liner. Can affect multiple benches. As I said before, we got narrow benches. So if it quickly goes over one bench, it'll spill onto the next and continue down several benches at a time. And there's obviously a lot of remediation costs involved with moving this material off the bench to get access again, filling in from the top. Production loss from not being able to leach any of these areas, or not being able to access further down the bench to leach more areas. And additional pop-offs can occur that will pull other drip tube off the side slope and pop those off, or the feed header. So here's some more pictures of washouts on VLF1. You can see we are in those freezing conditions on the left there, and created quite a bit of deep gouge out of the leach pad there and washed onto that bench, totally blocking off that lower bench. On the right, the picture shows the drip tube were pulled off on the sides of where it was actually came off at, so it pulled down multiple drip tube, and that caused more of a washout.
Zach, we're not getting any slide advance. We still have the plan view with the starting with the first line, 2 valley fill leach pads, VLF 1 and 2.
Let's see if I can get this to work.
And I think we're still looking at the video, but it's paused.
Yeah. Okay. Thanks.
Yeah, that looks more like a PowerPoint. Yeah, now it's advancing.
There we go. Okay.
Side slope washouts.
Okay, thank you. So this is what I was talking to earlier. Not going to read through all of that again, but you can see the image of the washout, one washout right there. And then this is the next couple of pictures that shows more of those washouts. One on the left covering the bench, and the other one with multiple lines being pulled off. So in solution for these washouts and stopping these pop-offs from occurring, we created 2 new excess flow valves. So excess flow valves work by isolating the flow through a pipeline after a flow set point has been hit. So these are the same kind of mechanism working for them, but a little bit different. So the first one was the check EFV, which uses a swing check valve and a modified bushing to accommodate a drip tube adapter. So these bushings, we had to modify them because you have a female end on one end and the male on the other, and inside of the male you need another female threaded connection for an adapter. So you do have to drill and tap on those bushings. But for installation, you have the check valve piece separated from the adapter, the bushing part. You thread the drip tube through the swing check valve, which holds the flap open on the swing check valve. And then you connect it onto the drip tube adapter as you would normally, which is connected to the feed header on the left-hand side. And then you thread the check valve onto the modified bushing, and that finishes your installation. So when the drip tube does separate from the adapter, it will pull or push the drip tube out of the swing check valve, allowing that flap to close. So it isolates the flow after that point. So here's a video of it. Holler at me if it doesn't come through. I'll just show that again. It happens pretty quickly. See drip tube coming off and the flow getting isolated pretty quickly. So the results of using the check EFV, we did find that we didn't learn a lesson with freezing. So once these did pop off in the isolated flow, the check valve assembly froze and cracked and sprayed. So we fixed that with a small hole drilled into the check valve on the underside of it, which allows a little bit of flow to go through the check valve so that it can continually have solution moving through it in case it's freezing outside and it doesn't freeze the whole assembly. We did find that, especially under lower pressure conditions, it would, the drip tube sometimes would get stuck in the flap in the check valve, but again, it was a minimal flow that was going through it. So not the blast of solution coming out of the feed header straight towards the side slope. So they tended to still prevent the washouts. We fully implemented using check excess flow valves for 2017 and 2019 before we switched to primarily injection drills, injection wells for production off of VLF1. So there was a significant reduction in our washout occurrences. They were pretty much every other day that we were having them as we were leaching all of that surface area, and we needed to keep all that area running with the water balance. So we went from about one every other day to about one every other week. So about an 85% reduction in the occurrences of washouts. The check valve has an advantage in that it's unaffected by scaling solutions because there's no wetted parts until it's actually activated. So we do have scaling in at the CCV site, scaling solution and debris. So none of that affected the operation of the check valve. We did have to construct a special steel template for making those bushings, as I talked about, just drilling them. So we had like a steel template. You could fit 12 of the bushings in there and then quickly drill and tap each one of those. Cost is a bit high, especially considering, one adapter is, maybe 25 cents or so. Costs about $14. Most of that is in the check valve part, but, enough of these add up to how much it costs to actually fix a washout. The next excess flow valve that we created was the Eddy EFV. So what this one is a T fitting with a ball in the 90-degree side, which is plugged off. So it's a PVC T. What we were using was 1/2-inch adapters and 1/2-inch fittings. So that's what we started with. So the balls rest down in the plugged side on the bottom side of the T. The T is screwed into the feed adapter with a nipple, and then the adapter is on the straight side of the T on the opposite end. So when the drip tube separates from the adapter, what happens is this increases the velocity through the T, which causes an eddy current or swirling motion that's sufficient enough to lift the ball out of the plug side of the adapter or the T, which then gets lodged inside the back side of the adapter, the inlet side, isolating flow. So, and with this one, it can be modified quite a bit. We were using Y-type fittings or T-type fittings, but the ball size and material can be changed. We initially started with glass marbles, found that they were not very uniform in size, so we switched to 3/16 steel balls, and sometimes we would put 2 balls in them or kind of extend it up and down this so you can get like a different height in the bottom, which causes it to go off at a lower pressure or a higher pressure, whichever you prefer. And the difference with this one versus normal EFV is that there's no flow path effect, so there's no directional changes or moving parts. So it kind of keeps a straight velocity through the T. It doesn't change the flow path at all. Here's a video. First video that I have. As you're seeing there is the drip tube being pulled off of the adapter. The balls in the bottom side of the T gets lifted up and quickly put into the inlet side of the adapter. This is a video of a Y-type fitting where the ball is down on the bottom side of that Y. You see the same thing with this one. It's at a lower pressure, so it takes just a split second more for the ball to lift up into it. Well, we got one more video here. This one's with a clear acrylic tee. So you can see in this one, it's like yellow orangish marble that you'll see lift up into it once the drip tube is pulled off of the adapter. Happens fairly quickly. Show that one again. Missed it. So you can hear it click into the backside adapter that isolates the flow. So the results from using the Eddy EFVs, we did, as I said before, use the 316 stainless steel mainly for cyanide compatibility and uniform size. Never fully implemented using these as VLF1, as I said, I switched over towards injection for the production off of that pad. But we did do a 6-month trial on one of the side sill panels. Throughout that 6 months, they operated fine. There was a few that popped off, and then once we tested them out after that time frame, they still worked. Scaling solution didn't really have an effect on the operation of the ball. That was something that we were worried about, because if it was scaling around it, that it would make that ball not lift up into the tee. What we found is it kind of swirls around it and kind of moves all that material up into it as it's kind of cleaning it out, and then eventually the ball will lift up into it. Quite a bit less cost with these ones, only about $4. In conclusion, we had quite a bit of washouts at VLF1 at CCNV. We're causing a lot of safety and environmental hazards, which resulted in a lot of costly remediation and production losses. So we were able to reduce those washouts significantly using the check EFE. Just kind of summarizing up what the two different EFEs, their advantages. So the check one is simplistic and it doesn't have any effect from scaling solutions. EFE, while not fully tested and implemented, was trial tested, and it is adaptable for various fluid types and flow settings. So it open up. I don't know if you have any time for questions or not. Appreciate y'all hanging through all the technical issues, and thanks for your attention. My email is down there below, zach.felkey@newmont.com.
Zachary, that was fantastic. What an elegant solution to a problem that haunts literally every heap leach in the world. Thanks for sharing that. We don't have time for questions, but you can reach out to Zach with his email, or he's also on Hua, the event app, if you downloaded that. So you can communicate that way. And Zach, thank you so much.
Thank you.
Our next speaker is live. So Patrick Nketia is going to be speaking about governance and management using KPIs. And I think I'm encouraged that we're seeing a lot of governance and ESG topics at this conference. So that's excellent. Thank you. All yours.
Okay, thank you. So I'll be talking about using governance and management, or using KPIs and early indicator dashboard to manage the performance of a heap leach pad. I mean, how safely are you going to manage the heap leach pad? So by using governance and KPIs, I mean, you can easily know how the pad is performing. Okay, so I'll give a little introduction and talk about key performance indicators, that is the KPI. Then heap leach performance, how we manage it using the KPI. Our reporting and communication, how we communicate to management, so that everybody will be in a clear note how the pad is performing. Then I will conclude or give some takeaway which we can use. So keep. Can you control that for me? From the first slide, yeah. Yeah, second, next slide. Okay, so Freeport McMoran, we use the KPIs to manage how the pad is performing or to monitor and mitigate significant safety and environmental risk. So the KPI and the early indicator dashboard helps to guide operations and technical team in managing the day-to-day performance and to drive clear communication and good practice action. So the KPI forms part of our operations and surveillance management. That's an OMS manual. So operations is aware of our KPIs so that whenever they're violating, they know, hey, we have this KPI set for operations so that they can follow the KPI. So the KPI focused on geotechnical stability in a long term, as well as good practice for maintaining stability over a longer period. So the KPI are compared to predefined alert levels. So we have predefined alert levels set to our KPIs. So resulting in scoring that is summarized in an early indicator dashboard for communicating the operational performance of the heap leach across our portfolio. So we have predefined alert levels or targets set for each KPI. So that we can easily compare if you're violating or we are within the design intent of the leach pad. So the KPI used in managing the safety performance of the heap leach are grouped into 7 main categories. And each category, we have subsections. So I'll go through that. So the first one we have is our phreatic surface. So talking about phreatic surface, you're talking about how our piezo elevations are performing and how many piezos are operational. You may have like 300 piezos, but are they all working? That tells you a good indicator of our pore pressure within the stockpile. Then we have crush ore material quality. So talking about that, we're talking about agglomeration. So we have KPIs and KPIs set for agglomerations. Our P80, all these KPIs, we have set target or threshold for all these KPIs. Then we have our fines content, which is 200 sieve minus 200 sieve, and our clay content. So we track all this so that to make sure we are within the design intent of the stockpile. Next slide. So we also have material movement. How much movement are we getting around the stockpile? How much movement for your foundation material which the stockpile is sitting on? So we have inclinometer and shape arrays to do that. Then we have surface movement using INSA. I'm not sure if everybody's aware of INSA, but that's a good technology we use in monitoring movement. Then we have surface movement using GPS. Then we also manage our ponds. Due to operational constraints, sometimes our ponds, sometimes you need to divert some PLS solution to our ponds. But then you should have a KPI set for that so that operation doesn't use that pond for their day-to-day diversion of PLS into that. I mean, you never know when you're going to have a major storm event. So your sump and your ponds should be always in a good shape to accommodate storm water whenever it rains. Then we have material placement. So when I talk about material placement, I'm talking about how much surface preparation do you do before you stack the next lift. So talking about, you need to update us on our stacking plan. So once the geotechnical engineering team knows our stacking plan, we know this is the area that we're stacking so that if there is an issue or if we stack material which is not favorable, we can easily go in there and check what is going on. Then we have roughness and PLS flow. How much application rate? So we have KPI set for our application rate. So are we violating the application rate? Then we have our PLS flow. How much PLS is flowing? I mean, after applying your roughness. So if you don't have enough PLS flow, then it tells me your roughness that you applied, you have a lot of roughness stuck in the stockpile, which is pore pressure problem. You don't want to increase your pore pressure within the stockpile. So that's something that we check too. Next slide. So we also check our monitoring and inspection. So site geotechnical engineer would do his site inspection, comes out with recommendations. So these recommendations, we have time attached to these recommendations. So were we able to resolve that issue within the time set by the engineer on site? Then on quarterly basis, we have our engineer of record, as the EOR, who also comes on site and performs inspection. So after the inspection, he comes out with recommendations, with deadlines for us to complete those recommendations. So it becomes a KPI set for us. Were you able to finish what the the EOR recommended? If not, that means you're violating the KPI. Then we also, on annual basis, we have a CLS team that we call Crash Leach Stewardship Team, where we have an external consultant who comes on site and also performs his inspection and comes out with recommendations. So all these recommendations comes with deadlines for you to accomplish it. So if you are not able to accomplish it within the time set, you violating the KPI. So how do we score our KPI? So the KPI scores are donated by descriptions and conditions that indicate trigger levels as follow. So when we say you are within limit, so that's how we score the KPI. If it is within limit, so it means that your operating conditions meet design intent. That's a good practice, so we should continue doing that. So if I score a KPI as approaching limit, so it means that your conditions during the operating period approach limit of design intent or expectation of good practice. So you need to increase level of attention for that particular KPI. If it exceeds limits, that means, I mean, you've violated the design intent of that KPI. So I'll give you a typical example of how we, a very typical example. Next slide. So this is a typical example of a scoring criteria for phreatic surface and monitoring. So for phreatic surface and monitoring, so your piezo levels, so I'm not going to read that, but that's if it is within limits, that is the description that we've set. That is the KPI that we've set for phreatic surface. If it is approaching limit, so those are the KPIs that we've set for approaching limit. So whenever your phreatic surface falls within that category, that means you are approaching limit. And if you've exceeded limit, that is the scoring criteria that we've set for that. Another example is like fines content minus 200. So if it is less than 10%, we are within our limit. If it is greater than 10%, but less than 15, we are approaching our limit. Anything greater than 15%, we've exceeded the design intent of the leach pad. So we need to take an action. Next slide. So reporting and communicating. So how do you report this? How do we go through all this? So data for individual KPIs are analyzed, interpreted, and summarized by the site geotechnical engineer on daily, weekly, and monthly basis using the scoring criteria of each type by the scoring criteria I gave on the previous slide. So yeah, so all this scoring criteria. So site engineer compiles the data and come out with the scoring. Next slide. So the second point, so this enables the site geotechnical engineer to track all these KPIs and take immediate action if any of them violate the criteria. So we don't wait till 2-3 months before if something is going wrong. So on a daily or monthly, weekly or monthly basis, we know we had this problem over here. So we easily tackle it before it's too late. So the next step is the scores and data are transmitted each month through our internal digital workspace to the engineer of record. So we have our engineer of record, EOR. So you summarize everything. This is sent to engineer of record, the leaching manager, and our corporate point of contact. We have a crash leach point of contact at corporate. So after you prepare your data, you put everything together, you transmit it to them. They go through to check if every numbers or whatever, all the KPIs that the scoring that you've given to each KPI, they go through to see if the scoring is correct. Once it's correct, once they are okay or comfortable with the KPI, they will give you the order or the acceptance to distribute it to final management. So if they have any problem, if they have any concerns, you need to address those comments before you transmit it to the for final distribution or to final management or all the stakeholders. So after EOR, POC, site geotechnical engineer, after they've gone through that, a summary report of Power BI is generated and distributed to all relevant stakeholders. So that is when after our EOR, everybody has gone through that, they give you the final destination to distribute it to all stakeholders. Next slide. So this is a typical example of reporting and communicating. So typical example, PAD. So for the month, your PAD, approach limit. Why did it approach limit? You need to explain why we approach limit. What did you do to rectify this situation, or what are plans that you have so that next time we don't have this scoring again. Then this is the final Power BI report that goes out to management. So you may see, so we have different crash leach pad. So if it is Southwest MFL, so you can easily go through, it makes it very easy for management to go through this. So which part are you assessing? If it is Southwest MFL, he can easily go into Southwest MFL. What month are we analyzing? If it is the month of August, month of September, you can easily go back to previous months and see how a particular KPI has been doing. So it makes it very simple. You also have to attach all your spreadsheet and calculations that you use in managing, in scoring this criteria. So it makes it very simple for everybody to go through. Next slide. So take away and my conclusion. So using the KPI score and reporting system at the heap leach pad site allows the site geotechnical engineer to analyze, review, and interpret data and take immediate action quickly and effectively. So it also gives a clear and accurate picture of the performance of their pad. Through the KPI score and the use of early indicator dashboard report, all internal stakeholders can understand the status and the performance of the heap leach pad. Data interpretation and visualization becomes very simple for stakeholders who are not directly involved in the day-to-day management of the heap leach pad. We have other management that's very busy. So with this reporting system, they get a clear indication of how the heap leach pad is performing. So then my last one will be, it also serves as a communication tool to advise on situation of concern and highlight areas that need support from leadership. So they go through this, so they can know, oh no, we have a problem over this KPI. So that is when they can also come in and support operations or any good ideas that they want to give to us. Yeah, that's what I have. Thank you very much.
Patrick, that was excellent. Thank you very much. And unfortunately, we don't have any time for questions, but you'll be around at lunch and people can
Yes.
talk with you. Thank you. Excellent, excellent. Two of my favorite things, KPIs and clear communications. Okay, our next topic, this is virtual. Is that correct, Melissa? Excellent. So this will be Oscar Meza discussing crushed leached ore characterization, response, and liquefaction. Excellent. There we are. I'm sorry. Oh, Oscar, can you say something to see if we can hear you?
Yes, yes.
There-
Can I?
Excellent. There you are. Okay. Thank you. It's all yours.
Oh, thank you. Good morning, everybody. It is a pleasure to be in this important conference. I hope my presentation will be on your interest, and thank you for attending this section. Today, I will present a practice-oriented methodology for seismic performance evaluation of leach pads under operation. This paper was developed in conjunction with Dennis Parra from Andes and Franklin Olaya. In South America, there are many challenges that must be considered in the design of hill leach. For example, complex terrain feature, high seismic activity, high altitude, among others. Therefore, comprehensive field and laboratory investigation must be carried out to achieve an adequate geotechnical performance, particularly under seismic actions. This paper presents a typical heap leach path to describe the geotechnical characterization and evaluation of crush ore, primarily based on the cone penetration test, CPT, but complemented with laboratory tests. The investigations and analysis are focused on the assessment of liquefaction potential for a given designed earthquake scenario. Supporting laboratory tests were performed, which results are used to determine the ore drained and undrained strengths. For the geotechnical characterization, we have analyzed the data obtained from 9 CPT tests carried out at different elevations and reaching depths ranging from 10 meters to 60 meters. The steps used for the characterization were based on the type of soil behavior I sub C of Robertson and Wright, 1998. The crush ore was considered to be sand-like if I sub C is less or equal to 2.5. Transitional if I sub C is between 2.5 to 2.7, or clay-like if I sub C is greater or equal to 2.7. And the saturation in the heap leach pad was inferred from the pore pressure dissipation test. With the result of the CPTs, areas which the dilative or contractive behavior have been identified. This identification was used to locate areas likely to experience stress softening. To define whether the behavior of the crush ore is contractive or dilative, the pressure proposed by Robertson and Cabal 2015 and Shuttle and Canning 2008 were adopted. Robertson and Cabal employs the clean sand equivalent normalis con-resistant QT-CS, where the limit between contractive and dilative response is QT and CS equal to 70. The approach of Shuttle and Canning 2008 employs the state parameter with the contractive dilative threshold located at minus 0.05. This is the resulting section from combining information from 9 CPTs in the past, following the previous methodologies. For example, the green areas represent sunlight or with contractive response. In contrast, the red areas are clay-like or with dilative behavior. We also showed the inferred piezometric level from the dissipation test. Through a geotechnical drilling campaign, the ore was sampled using Shelby tubes to carry out a laboratory test, which consists of index tests, one-dimensional consolidation test, consolidated undrained triaxial test, and hydraulic conductivity, which result are used to determine drain and undrained strengths. The undrained stress envelope was initially estimated from PQ stress pass derived from CU triaxial test, as shown on this figure. Then the trends in the data were verified with a simple Kankle-based expression for a normalized undrained strength, with the found to vary within 0.26 to 0.28. In addition, CD triaxial tests were considered to evaluate the peak drain strength of the crushed ore. The drain friction angle is found to vary within 35 to 38, which is consistent with the drain friction angle of angular clean sand. The laboratory data from fine and coarse ore are proposed in a similar way to obtain the table here on the left, which summarizes the parameter estimated for the crush leach ore according to its behavior. One-dimensional nonlinear time domain side response analysis were carried out of at each CPT location using deep soil. The design ground motion is the 175 years uniform hazard spectrum with a magnitude 8.8, as shown in the picture on the left, where 7 escalate motion are also shown. G over G max and damping curves for the fine and coarse ores were modeled with Darendali 2001 formulation, while the granular foundation was modeled with the curves of Meng 2003. Also, we analyzed the effect of modeling the low permeability interface between the foundation and the ore using the procedure of Yegian 1988, but smaller amplification were obtained compared to the model without interface. The results obtained from the side response analysis are shown in the figure on the right. For CPT-8 is an example, where the sun-like, transitional, and clay-like are shown with different colors. The peak of the distribution of peak horizontal acceleration within the heap leach path is represented in this figure for the 7 ground motion used in this study. The variability due to the ground motion characteristic and crash leach or geotechnical properties in the acceleration distribution is highlighted by a lower and upper bounds, which range in the order of 0.1 G. It can be seen as significant acceleration amplification is observed at the depth of 50 meters, to which corresponds to a layer of granular ore sandwiched by two relatively thin layers of softer materials. A similar effect is observed at the depth of about 40 meters. At the surface of the heap leach pad, its overall amplification factor is around 1.25. The earthquake-induced cyclic shear stress ratio at the same CPT location is shown here. Similarly, the variability in the CSR is highlighted by the lower and upper bounds. It is observed that the variability in the CSR is smaller than the variability in the acceleration in the wall profile. Also, the CSR is significantly higher in the top of the heap leach pad, and the surface of overall amplification factor for the CSR is 2.7. The liquefaction potential of the crush leach ore was assessed using the stress-based method proposed by Sid and Idris in 1971. The simplified approach compared the cycle stress ratio CSR to the cycle resistance ratio CRR to obtain the factor of safety against liquefaction, as shown in this figure, in this equation, sorry, where key sigma is the correction factor to significant effective confinement stress, and MSF is the magnitude scaling factor. The CSR profile was obtained from the site response analysis, while the CRR profile was Robertson and Cabal 2015. Importantly, clay-like ore was initially assumed non-liquefiable. For this material, the evaluation could follow the procedures of Ray and Sancio 2006 and Idris and Boulanger 2008. The first two graphs show if the mineral have a contractive or dilatant behavior. The brown points of the first graph represent the sign-like behavior, and the green points transitional behavior according to Robertson. Likewise, the second graph indicates the values greater than the red line present a contractive behavior according to Schuttel and Canning 2008. And finally, the liquefaction potential of the saturate ore is observed in the last graph. For CPT8, it can be seen that the sunlight and transitional behavior represent values of factor of safety against liquefaction less than 1.1, for which they tend to liquefy. These areas where no factor of safety correspond to clay-like behavior. Finally, as a result of the characterization of the ore and the liquefaction analysis, the ore can be distinguished by coarse ore that has a sand-like and transitional behavior, and the fine ore as clay-like behavior, in addition to knowing if it has a contractive or dilatant behavior. For this case study, the data of 9 CPTs show an important variability in the behavior of ore in heap leach pad, as can be seen for a contrasting color representing different per response. The liquefiable zones are represented by the black hashing. and they are not predominant throughout the depth of the CPT, possibly due to the higher CRR values and the predominance of clay type ore. We also see that liquefiable areas are not connected laterally. Summary, the I sub C parameter classifies the ore as sand-like, transitional, or clay-like. QT is an state parameter used to distinguish response between dilatant or contractive. The response analysis suggests that significant acceleration amplification can occur within the heap leach path. The combination of multiple response analysis can be used to inform the liquefaction trajectory analysis. The effect of the interface between the foundation and the ore using the procedure of Jagian was found to be not significant. For ore with I sub C greater than 2.7, the procedures of Ryan Sancio 2006 and Idris and Boulanger 2008 are recommended. Thank you.
Oscar, thank you very much. That's actually a topic close to my own heart. This is very good data sharing, good explanations. We don't have time for questions. We are running a little bit late, but if it's okay, Oscar, is it okay for people to reach out to you by email or via the Huva app that's for the event?
Yes, the question can send me by email, please.
Perfect. Thank you. Thank you very much. Okay, our next speaker and the final speaker for this session, and in fact, final speaker for the individual sessions is because after lunch we'll be going to a keynote speaker, is Franco Sánchez. He's going to talk about statistical functions for cost estimating. Holy cow! Cost estimate. Okay, I'm not going to even try again.
Okay, good morning, everybody. My name is Franco Sánchez, and it's a pleasure to be here in this important event. And I would like to thank to the Congress and Andes to this opportunity to present this article entitled Statistical Functions for the Development of Heap Leach Pads Cost Estimation. So the construction of leach pads in Peru has increased significantly over the last decades as a result of the low cost of construction and operation associated to the exploitation of low-grade ore deposits. Different works are required for the construction of heap leach pads, such as earthworks, construction of the underground system, installation of the liner system and the leachate solution collection system, and finally the placement of overliner on the lined area. Currently, there are no document records of the costs associated with the construction of heap leach pads in the Andean region of Peru that will serve as a basis assessing the feasibility of this type of projects in such regions. Therefore, it is of major importance to have a statistic tool, such a cost-based function that allows to estimate construction costs at the conceptual level with a graded accuracy in accordance with the surrounding environment. Okay, this is the contents of my presentation. First, the objectives, then we are gonna review the research methodology, the data collection, the data processing, the statistical analysis, then the results of this investigation, and finally the conclusions and the recommendations. Well, first, the objectives. In Peru, mining facilities and especially hill leach pad construction is mainly carried out in the Andes region, where the construction face many adverse and aggressive environments, which have impacts on construction costs, both for the start of operation and for the expansion of the following phases of the leach pad. Therefore, the purpose of this paper is to provide a useful tool for the construction cost estimation of heap leach pad project under certain conditions. For the development of the aforementioned tool, an analysis of projects executed in Peru in the last 10 years was carried out to generate cost functions of the incidental activities with the highest cost in the construction of hill leach pad and for the main complementary facilities for the start of operation. So in order to this, we have the first objectives to introduce a statistical methodology that allows us to obtain a reliable estimation of the cost of the various components of hill leach pad in the Andean region, so that it can be used as a tool for a more accurate estimation of conceptual costs. And then use a statistical analysis like chart, etc., to determine the equation or intervals that will allow to determine the estimated cost a priori of the component of leach pad research methodology. Okay, proposed analysis are intended to do interference from population values, proportion, means, based on a sample. If you want to estimate a proportion, you must know the level of confidence or security, the precision you want to for the study, and an idea of approximate value of the parameter you want to measure. For finite population, the sample size is determined using this equation, where n is the total population size, zeta is 1.96 squared for the 95% level of confidence, p is the expected proportion, q is 1 minus p, and p is the precision. In our case, p is 5%, q is 95%, and d is 3%. So in our universe, it's made up from a minimum of 19 projects. This means that it will only be necessary to evaluate 19 projects with a security of 95% and with an accuracy of 3% is desired. Okay, data collection. So the data used correspond to the information collected from 21 mining projects of leach pad costs found in the Andes database. It should be known that the cost of investment projects correspond only to direct costs. Local taxes, profits, general expenses, supervision, CQA, among others, are not included to avoid fluctuation inherent to these items and obtain closed cost function data, except for the statistical analysis of the total capex of the project. Variables were identified for each of the components of the leach pad project after being identified in the Andes database. In the table, we can see the number of projects completed per year, which has the highest incidence in the 2019, before the pandemic. But we also have data from years of the pandemic and the current global economic crisis. It's important to say that the data of the projects, it consists of the detailed models and of the leach pad designs and their detailed construction budgets. Okay. Then the data processing, we process data from these systems. Each of the main characteristics of each system of heap leach pad projects was identified, the systems considered were foundation, surface grading, liner systems, solution collection system. Any type of pool not being included in the scope of this study. Okay, we have many variables found. We obtain values of different variables, such as if the leach pad is a new one or is an expansion, the capacity, the density, the volume of ore, the area of the crest area, others such as the land areas before being impacted, the foundation areas, the grading areas, in addition to the areas sectorized by the slope, the perimeter, the geosynthetic that is used in the leach pad, the linear methods of soil drainage and solution collection pipes, among others, according to the design, technical, and economical values. Okay, a first estimation of the standard deviation and the average updated cost or average updated unit cost as appropriate was performed to detect string records in the data sample that might distort the results. Consider Chebyshev's theorem, the range average plus minus 2 standard deviation was set as a limit. All data outside this range were removed from the sample. Okay. Upon discarding the sample data that exceeded the limit range set, average plus minus 2 standard deviation, many tables were drawn to different variables. In each table, we set a first column containing the data regarding to the system characteristics, for example, capacity or dimension, height, volume, pipe length, etc., which correspond to the independent variable, the X variable. And a second column contains the information regarding to the cost or update unit cost, which correspond to the dependent variable, the G variable. For example, the capacity versus capex, or the cut volume versus cost, the foundation area versus its cost, the under the paint length versus its cost, etc. Consequently, the software Microsoft Excel was used to determine the mathematical models for cost functions that depend on a single variable, for which the data obtained from the data processing was input. Whereas the example in this graph, where we show that the correlation coefficient was about 0.7. However, for the equations that had correlation coefficients below the 0.7, we try to ensure that there could be a consistent correlationship by using more variables to fit the equation. To this end, to make this goal, we use variables that may have an impact on the cost estimate and that could obtain correlation coefficients about 0.7. And finally, again, we discard charts with correlation coefficients lower based on the fact that the data set has a minimum or a strong level of dispersion. In the case of many variables, we use the software GMDH chip 3. Okay, the results. Here I show the result for foundation equations. The foundation is the surface where the heap leach pad will be founded and is estimated based on geotechnical field and laboratory investigations. The cost includes clearing and grubbing and cutting of topsoil and untreated materials until the depth of competent foundation is reached. we can see that we have an equation to obtain the foundation cut cost by calculating the volume, which is what cost engineer usually done. But we also have an equation to calculate the foundation cost by measuring the area. Where we were also able to find the equation for the volume of the foundation that depends on the site area, the average of depth of foundation depth, the foundation area, because it's not the same area as the site area, no? Okay. This is the results of the surface grading. The surface grading is different to the foundation surface because it's the final surface where the heap leach pad liner will be a gradient be configured towards point of concurrence for the drainage and curve of the leached solution to the process pond. Costs include cut and fill works to achieve the level set in the leach pad design. For this case, we have calculated two equations. One equation for the material and another equation for the fill. Both equations depend on the volume and is quite consistent because it's how usually the grading cost is calculated. Okay, then we have the under drain system function. The under drain system is function is to capture groundwater flows originating within the limits of the heap leach pad and divert then underneath the liner system to the under drain ponds located downstream. Costs include excavation for the drain constructions, installation of pipes and geosynthetics, placement of drainage material. In the case of sub-drain system, we have calculated the cost with respect to the pipe liner meters the project has. A function could also be obtained if we calculate the drainage cost dependent to the lined pad area. It could be done in the next investigation. Okay, liner system functions. The liner system function is to serve as an impermeable barrier to prevent leakage of the leached solution into the natural ground. Costs include earthworks for the placement of the low permeability zone or installation of the GCL and the installation of the geomembrane. We can see that this equation has two variables, the lined area and the lined area with a slope greater than 25%. Because on these slopes, we use GCL instead of low permeability zone. So the cost is changing. Okay, the solution collection system functions. The solution collection system function is to collect and quickly convey to the leached solutions accumulated within the bottom of the leach pad to the operating pond. The cost includes the installation of the pipes and placement of the drainage material. In the first graph, we have found a relationship between the length of the solution collection pipes and the area that has a maximum of 10%. Then we have found a relationship between the cost of the length of pipe, the pipe's length that we have in the project and the cost of the solution collection system.
Hey, Franco, can we wind this up in another slide or two, please?
Okay. we have the overlaying functions, then the capex, total capex functions that when in the first equation, it depends on the side area, lined area, average foundation depth, and slope greater than 40%. In the second equation, depends on the volume, the longest footprint, and the leach pad crest area. Okay, conclusions and recommendations. That the cost function obtained provide an order of magnitude estimate of the potential cost associated with the construction of a hill leach pad project. Set functions have a good correlation and were obtained using a single variable. Nonetheless, several variables can be considered, such as classification of areas according to the set range of slope gradients to obtain a function to determine a raw estimate of cost. The cost associated with the most frequent activities performed during the construction of a hill leach pad, such as foundation, grading, underground, solution collection, liner, and overliner, were obtained in this research. The AAC International classified the estimates by 5 classifications. The development of cost function is applicable for the class 4 and 5 estimates in accordance to the cost estimate classification system by the AAC International. It constitutes a baseline to achieve accuracy in cost estimate range from -50% to +100% variance. This is the last one. It's recommended to use the largest possible source data to broaden cost function, not only for the location of a new mine or its expansion on a typical landing areas of Peru, but also considering the complexity and unique characteristics of each region in the world, such as Latin America and North America, among others. It's recommended to look for different variables as well as the various correlations existing between them, using methodologies focuses on data analysis such as neural networks and other technologies. Although cost functions presented in this paper are limited, it's advisable to conduct research on this subject so as to serve as tools in the mining industry and provide benefits from the conceptual engineering level, and certainly save time and resources during the following engineering stages of the project. So this is the end. Thank you very much for the opportunity. Thank you.
Franco, thank you. Thank you very much. That's an amazing amount of data and hard work behind that. Thanks for sharing that. We do not have time for questions. I'll invite people to reach out by email. There's also a couple of Andy's representatives here today, including Silverio, who just stood up, so you can find him in case you have questions. So thank you. Now we have lunch. We have a bit of a compressed schedule. Lunch is ready, and there's now should be little or no line. We reconvene here at 1:15 for the keynote.